In this video, we're actually not going to talk about physics, but we are going to talk about a skill called proportional reasoning. This is something mathematical that we are going to be doing with our equations all year. So today we're going to talk about what exactly is proportional reasoning, and we are going to start to apply it to our kinematics equations from Unit 1. And one thing to keep in mind, this is just an introduction to proportional reasoning. This is a mathematical skill that we are going to be doing and working with all year, so there is no pressure to try to master it today. This is just going to serve as an introduction, but we are going to get practice pretty much every single unit. So proportional reasoning is a type of math and logic that allows us to see how related variables, so variables that might be related to each other in an equation, might change or not change together. So let's look at these examples kind of from Algebra 1. So we have an equation y equals 4x, and I want to know if x is tripled, if I make the value of x 3 times as big, what is going to happen to y? Well, in order to figure this out, there's two basic ideas that we need to consider about equations, specifically what this equal sign means. So equal means that, well, y is always going to be equal to 4x over whatever domain is described. And if there is no domain, that means that this always has to be true from negative infinity to positive infinity. Y is always equal to 4x. We cannot violate that. And in order to keep that true, whatever you do to the right side of an equation, so let's say we add 1 to this right side, well, we have to do the same thing to the other side. We have to add 1 to the other side. And that's how equal signs and equations work. So knowing that, let's see what happens when we triple the value of x. We make it 3 times bigger. So over here, I'm going to, instead of x, write 3x like this. Notice I've tripled it. Now, writing this, I've just violated the basic laws of algebra. Y cannot equal both 4x and 4 times 3x or 12x at the same time. These both cannot be true. So I have to do something to the second equation to fix it. Well, I multiplied the right side of the equation by 3, so I'm going to have to multiply the left side of the equation by 3 as well. Notice this equation, 3y equals 4 times 3x. It looks the exact same as this. Those 3's can just cancel out. But notice when we triple x, y also ends up tripling. What we do to x, we also do to y. Let's look at this second example. Same basic idea, y and x are related, but notice it's now 4x squared. So if x is tripled, again, we are tripling it, what happens to y? Well, on this right side, we have 4 times 3x squared. And it might look like we have tripled the right side again, but actually, if we simplify this, 3x squared actually turns into 9 times x squared. We have to square both the 3 and the x. Just to think about this again, x squared actually is x times x. We don't really write it like this anymore, but that's fundamentally what x squared is. So really, when we triple x once, we're actually tripling both of these. So it's 3x times 3x, and that's how we get the 9. We multiply the 3's together, and then the x squared. So notice, we originally have 4x squared. Now we have 4 times 9x squared. This 9 is a new factor. We have increased the right side by a factor of 9, so we need to increase the left side by that same factor. 9y equals 4 times 9x squared. Well, that's the same as this equation here. Again, notice those y's we can cancel back out. So because this is a quadratic relationship, if x is tripled, y is actually going to be multiplied by a factor of 9. Again, all we're doing is just making sure the left side equals the right side. All right, now let's look at this third example, because this one changes things up a little bit. Given y equals a times x, we are still tripling the value of x, but in this case, y does not change. It is a constant. So notice in this equation, y on the left side, I'm going to draw a 1 here because we're keeping it the same. We're multiplying it by 1 is equal to a times 3x. Now, I've multiplied the right side by 3. Normally, we would multiply the left side by 3 as well, but we can't because y can't change. So something else has to change. A is going to change by some sort of factor. Notice the left side didn't change. So overall, we've multiplied by 3 on the right side, but we need to undo this 3. And in order to do that, a is actually going to be cut in a third. 1/3 times a times 3x, the 1/3 and those 3 actually cancel out, and we're back to ax. So notice a would be cut in a third. Again, all we're doing is just making sure the left side equals the right. Then finally, this last example, we have this squared here, but it's the same basic idea. X is now going to be quadrupled, so we're going to multiply that by 4, but a again does not change. So a stays the same, and x is going to be quadrupled. Well, I've multiplied the right side by a factor of 4, so the left side also needs to be multiplied by a factor of 4 by changing this y. But kind of like we saw up here, whatever factor I change y by is actually going to happen twice. So we really have to ask what squared is going to give me a factor change of 4. And that's actually going to be 2. So 2y squared, this ends up turning into 4y squared equals a times 4x. And notice those 4's can cancel out again. Again, we're just making sure the left side still equals the right. So if x is quadrupled, y only doubles, like this. Now, this kind of math, this is just the basics from Algebra 1, but this is what we're going to be doing with our physics equations as well. So let's revisit our kinematics equations, and this is an example that I want us to look at. So we have a cheetah, and it accelerates from rest at a rate of 2 meters per second every second. And we can use this information to determine the velocity and the displacement of this cheetah at all of these following times. So if you want to, you can make some predictions, you can pause the video, try to fill in this table mentally. If not, I'm just going to fill it in for us. So for velocity, we want to use our velocity function. V equals initial velocity plus acceleration times time. Notice our initial velocity is 0, so that term is going to go away. And our final velocity is going to be our acceleration, 2 meters per second squared times time. So to get this velocity column, I just took all of the times and I multiplied them by 2 meters per second squared. For this displacement column, now we have to use our displacement function. Delta x displacement equals initial velocity times time plus 1/2 at squared. Again, the initial velocity is 0, so that term is going to go away. So our displacement, delta x, is going to be equal to 1/2 of our acceleration, 2 meters per second squared, times time squared now. So to calculate this displacement column, I took 1/2 times 2 times the time squared. And that gets us all of these values. Now, these are pretty easy calculations, but what I want us to pay attention to is the fact that there is actually a deeper pattern going on here. Notice when I double the time from 1 to 2 seconds, notice what happens to our velocity. Our velocity also doubles from 2 to 4. Notice when I triple the time, I make time 3 times as big, our velocity also triples, 3v. Seems like whatever I do to this variable, I also do to that one. I have to keep the left side and the right side equal. So there is this pattern of whatever we do to time, we do to our final velocity. So to finish up this table, we double time. Turns out our final velocity is doubled. We triple time, we triple our final velocity. But there's also a similar but slightly more complicated pattern with time and displacement. Notice when we double our time, our displacement actually doesn't double, but it quadruples. It gets 4 times as big, or another way to think about this, it gets 2 squared times as big. When I double time, I do something quadratically to displacement. Same thing, when I triple time, notice our displacement gets 9 times as big, or 3 squared times as big. And even if I quadruple the time from 1 to 4, you'll notice now my displacement gets 16 times as big, or 4 squared. So it seems like now there's some sort of quadratic relationship. When I double time, I quadruple, or 2 squared, my displacement. When I triple time, now I'm going to 3 squared our displacement, or 9 times. There seems to be a fundamental proportion going on based off of these equations. And this is what's going on with proportional reasoning. So with velocity, If the object starts from rest, so that was the situation we looked at with the cheetah, so this term goes to 0, and the acceleration is held constant. So this is always the same value. There is a proportional relationship between velocity and time. Whatever you multiply time by, like maybe a factor of 2, velocity will be multiplied by the same factor. We have a very special word for this. This is called directly proportional. Now, proportional just means two things are going to relate to each other. They're going to grow or shrink together, but directly proportional means they grow or shrink at the exact same rate. So again, I double one, I double the other. I triple one, I triple the other. And that relationship exists between velocity and time as long as acceleration is held constant. Now, the symbol that we are going to use to represent this is this symbol right here, this kind of fish-looking thing. This is the proportionality symbol. So we would read this as velocity is proportional to time. Notice this is not an equal sign. We're not saying velocity is equal to time. Let's go back to this example. Notice velocity and time, they're not the same value, but they are proportional. They grow together. So let's see an example of this. How might you see this in physics? So let's say we have a car that accelerates from rest. After a time t, we don't know the exact time, but some time t has passed, the car is moving at a velocity v. So you've started from rest, you've hit your gas pedal, and you've let some time pass, and you glance at your speedometer, and v is how fast you're moving. I want to know how much time does it take the car to reach a velocity that is 3 times as big? Well, we can use proportions to answer this. We can start with our velocity model. Again, we're going to set initial velocity equal to 0 because we start from rest, and that means v is equal to at. And again, since acceleration is held constant, that means velocity is proportional to time. If we have a velocity that is 3 times as big, time also has to get 3 times as large. So it's going to take 3 times as long to reach a velocity 3 times as fast. We can also show this relationship with our graphical models as well. So let's model this with a velocity time graph. Velocity, time. So we are going to accelerate from rest at a nice constant rate. So we're going to have a nice linear velocity time graph. Right here is a time t, and here is our velocity v. Well, if I increase my time by a factor of 3, so here's 3t, and then here's 2t, increase this up. Here is our new velocity here on this y-axis. Well, how far up is this? Notice if we just kind of draw all of these nice lines, every time I increase the time, I'm going to increase by a velocity. So here is 2v, here is 3v. So notice 3 times the time, 3 times the velocity. We can also show this with an acceleration time graph as well. I like this one. This one's pretty cool. So if we have a constant acceleration, that's going to be a nice horizontal line. Here is t, here is 2t, and here is 3 times the amount of time. This area underneath the acceleration time graph doesn't actually give us our velocity, but does give us our change in velocity. And since we know where we started from rest, we can use this to relate to the final velocity. So notice we have this area of this rectangle. Now, if I triple the amount of time I let this accelerate for, notice we have tripled the base of this rectangle. This area here is now 3 times as big. This total area has a 3 times the area, so is 3 times the change in velocity. Notice all 3 of these are showing the exact same idea. We just have this new representation with these proportions. So there's a linear relationship between velocity and time. Now this isn't something you have to have memorized. Notice the fact that this equation is linear, it tells us that that is the relationship. So really we're just reading a little deeper into what the equation says. One last equation I want to cover, because it's a slightly different relationship, is our relationship between displacement and time. If we remember back to the table, slightly different relationship. So we have our displacement function right here. As long as the object starts from rest, which means again that term is 0, and the acceleration is held constant. So we are not changing this value. Then there is also a proportionality between displacement and time. Basically, anything I do to time, so if I double time, that factor gets squared, and displacement is going to increase by a factor of 4. If I triple my time, remember that's going to get squared, displacement is going to change by a factor of 9. This is a proportional relationship, but it's no longer directly proportional. We're going to call this a quadratic relationship because this is a quadratic equation. And the way we write this relationship here, delta x, again, is proportional to, this is the symbol for is proportional to, time squared now. It's proportional to the square of time. And what this means is whatever change we make to time, we square it, and delta x will change by that factor. So again, if I multiply time by a factor of 10, displacement will increase by a factor of 100. If I multiply time by a factor of 5, then displacement will increase by a factor of 25. That is just inherent in this relationship. So again, let's look at this in context of a problem. So again, a car accelerates from rest after a time t. The car has discovered a distance delta x. I want to know how far has the car moved after accelerating for 3 times the amount of time. So using proportions, again, we'll use delta x equals 1/2 acceleration times squared. Again, we're leaving out that initial velocity term, so we're accelerating from rest. That means displacement is proportional to time squared. So on the right side, if I triple time, okay, I've changed this by a factor total of 9. So that means on the left side, I also have to change this by a factor of 9. Notice I'm showing this with the proportionality symbol. You don't necessarily need to do that. You can also just do 1/2 a 3t squared like this equals 9 delta x. You can keep these other things here, the 1/2 and the acceleration. Just keep in mind these are constants. They're not affecting these proportions. So 3 times the time, 9 times the displacement. I really like showing this one with a velocity time graph as well, because if you don't believe me that this works, the velocity time graph is great. So again, we're going to accelerate from rest. Nice constant slope for constant acceleration. Here is t, and here is 3t. So the displacement now is going to be the area underneath this triangle. Notice here is the area delta x for a time t. And if we were to calculate this bigger area of this giant triangle, well, remember, the area of a triangle is 1/2 base times height. Well, this bigger triangle has 3 times the base, t to 3t. So we are increasing the base by a factor of 3. And the height of this triangle from v to 3v also increases by a factor of 3. So if we triple both the base and the height of this triangle, notice those 3's combined, and our area is actually 9 times as large. Consistent here. 9 times the area, 9 times the displacement. My other way I like to show this, we can also break this bigger triangle up into a bunch of smaller triangles. So I'm just kind of subdividing here, separating into a bunch of smaller triangles. Notice here is one triangle, one displacement. Well, now let's count all the triangles for the big one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Wow, really not shocking. 9 more triangles, 9 times the amount of triangles, 9 times the amount of displacement. Notice all of these models are going to be consistent.